Hi, Net 125 students. I'm creating a short video for you, or well, it may not be that short, but it's the first part of Chapter 3. I'll create another video for the second part of Chapter 3. So this video will cover 3.1 through 3.23. So we'll talk about communication and standards. So I'll go ahead and kind of jump to this, and again, I just want to talk to you just like I would in a classroom setting and talk to you a little bit about some of the concepts here. So the first part of the chapter talks about human communication, and this is how we would communicate with each other. Think about the telephone system here. So in a regular telephone system, you would have these components. So you'd have a source and a medium or a signal, then you'd have a receiver. Okay, so your source, somebody has to pick up the telephone. You had to have a cable and the different mediums from one end of the cabling to the receivers, and then of course you have the receiver. The other component that's not really mentioned here, you have the source, the medium, and the receiver, would be a protocol. Okay, so this is something else we'll talk about this in this chapter. So they show human communication on the first part, which is no different than regular communication. So in addition to having the source and the medium, the receiver, the fourth component that I would add there is a protocol. Protocols are talked about in this chapter, but if you're having a source, medium, receiver, so you have somebody pick up the telephone, you have somebody answer the telephone, that's great, but if you're not speaking the same language, then you're still unable to communicate. That's why a protocol is so important. So that's the same way that communication occurs between two devices. They both have to have the same protocol in order to communicate. So that's a very important component. This is a good example of that. So look at this kind of jumbled up sentence. Well, if you translate it, then it actually makes sense. So that's a good example of how a protocol works. A protocol, we really think of a protocol as a certain set of procedures, so everybody kind of knows what the rules are and knows what to follow. So here's some things that are actually talked about in protocols, so you know who the sender and receiver are. They speak a common language. Speed. So you don't want to have someone talking faster than someone else can digest what they're talking about. So the speed and the timing of delivery is important. Confirmation or acknowledgement requirements. So if someone quits talking at the other end, maybe the signal dropped, maybe they fell asleep on you, who knows. So so confirmation or acknowledgement, and that all those components are important parts of a protocol. And the nice thing about a protocol is all these things are defined ahead of time. So you're not guessing how it works. It's just clearly defined. So that way, if two devices are using a protocol, they know the rules when they get started. Okay. They also encode the messages a certain way so that once the sender sends it, okay, the destination can decode it and understand what's sent. Okay, not unlike, say, if you were younger and wrote messages in, say, a format that only you and your friend could understand. Okay, that would be a good example of that. Or if you're referring to just traditional letter writing, there's different formatting structure here. So you know the recipient's address is here. The sender's address is here. The format of the letter is in a certain way. Okay, that's the way things happen in the communication process as well. So the destination of the person, the source of the person sending it, okay, that's done in your addressing. It's encapsulated a certain way with different types of identifiers, and then the actual information, and then something to indicate that that's the end of the process. Okay. It's just kind of like the different parts of a letter. You have the header, and you have the last part where you sign your name, and you know that that's the end of the letter, for example. Okay, so kind of breaking this down a little bit, if you're talking about message size, whether you're talking about computer communication or human communication, you know, there's only so much maybe a person can process. So message size is an important process. and so is the timing. It's referred to when in your message timing, the access method. So how is the information going to move about on whatever type of medium? Are they going to fight for access? Are all the devices going to just take turns? Okay, so that would be the access method. So how your data actually accesses whatever medium you're using. Another component is flow control. With flow control, how much data is the sender going to send? Okay, so you don't overload the receiving end. A response timeout. So the response timeout indicates, well, how much time are you going to wait before you hear from the device again, before assuming that it's no longer communicating with you. And then you have different formats. So this is message delivery options. You see unicast, multicast, and broadcast. With unicast, you're speaking one person to one person. So same with the device, one device to another. With multicast, one person or one device is speaking to a group. With broadcast, they're speaking to everyone. So those are your three that you'll need to know, these message delivery types. Unicast, multicast, broadcast. Think of the prefixes if you know your prefixes. So uni as in unicycle, or say one wheel. So that would be unicast message. Multi meaning more than one. Broadcast would be message to everyone. Okay. So again, protocols help us determine how we're going to talk to another person, another device, if we're all following the same rules and procedures. So in this case here, people know to use a common language. They wait their turn, they signal when they're finished. All this is kind of predefined here. So this is how your protocols work. Here's an example here. I will send this message using an IPv4 header. This one, I can forward it because I understand that. I can accept it because I understand IPv4. That's the format or the structure process. They're all on the same page, so it makes it easier. Here it says, let us all agree that if one of our pathways is down, we will notify all devices. So again, all this stuff is predefined. So they know what's supposed to occur, and then again, they know what happens or what needs to happen if it doesn't occur like it's supposed to. Now, one of the types of protocols that's the most popular is this TCP/IP protocol interaction, which is how the web is based. TCP/IP, and this is the protocol stack here. Okay, so we're looking at the application layer, transport, internet, and network access. So the application layer, if you're talking about a web server and a web client, is HTTP. So you type in HTTP:// and then the address whenever you're actually beginning or initiating the communication process. The next step, what happens from there, is the TCP protocol is used. Okay, so it identifies the port number associated with the HTTP. Then it has an IP address using the Internet Protocol. And then Ethernet would add the MAC address of your network interface card. And then once it's received by this device and it sends something back, it will go through the same process in order to send. Here's another look at the TCP/IP protocol model. Okay, this protocol model is open standard, so it's available to the public. That's what it's kind of understood, that the web traffic all flows using the TCP/IP model. So you see lots of different protocols here. Don't be expected to know all these. We'll talk about some of these more in the next couple of minutes here. But application layer, if you think about this, the application layer, look at all these right here. So these are the ones that you're actually kind of interacting with. This is what I would say closest to the user, which starts the process. Because as each computer is trying to communicate with another computer. It starts here at this application process. So you would begin the process by typing HTTP colon whatever. Okay. And then before it sends something out an interface, it needs to add a protocol to identify the type of traffic. Give it an IP address, and then here is where we use the Ethernet. We get a MAC address on attached to the data, and it goes out the NIC and then eventually the cable. So it goes down this model. When it's received at the other end, what happens is it receives it on the cable and kind of checks the MAC address, looks at the IP address, and sorts out the traffic based on whatever protocols used, and then it gets up here and you actually see your web page. It accesses your web page. So TCP/IP has been used for a while. I won't go through this whole slide with you, but you could actually kind of go through this. I think I made reference to this in the past video about how long the internet has been about. So it started around 1969 by the U.S. Department of Defense. So you can review this timeline here and see the development of the TCP/IP. So here is another slide on the TCP/IP model, and it's broken down. These are interactive links that you can click on, and it'll tell you what each of the protocols does. So I will kind of let you do that on your own. I would encourage you to use these as you move throughout your studies in this class and other classes especially. You'll really be using these a lot. DNS, domain name server or domain name system. Okay, this is what's used in order to keep track of an IP address and its actual name. So this is what we would use. If you're typing in the pittcc.edu, it actually goes to a server to figure out what the actual IP address is. Okay, and then it tries to figure out what location to go to from there. Okay, so it attaches a name so that we don't have to go around remembering what the IP addresses are of all the devices we're trying to communicate with. You have host configuration, so BootP was developed and then DHCP is used now based off of the BootP, so dynamically assign addresses on a network. We have our email protocols, we have file transfer, we have web. Your transport layer, you have UDP, you have TCP protocols. I guess just kind of sum these up, your TCP protocols are more reliable. Again, this is what you use on the internet. They're reliable because they let you know if something doesn't get from point A to point B. UDP does not. So that's the biggest factor in both of those. But again, you can click each one of these, it'll tell you a little bit about those. UDP is great for streaming services. So if you have video or voice where you don't need an acknowledgement every single time something is sent, you'll use UDP. But TCP, if you need reliability, like to know your email didn't get somewhere, yeah, that's where TCP comes in. Your internet layer, these are your IP addresses. Support, ICMP is ping. So you've used ping, I believe. If not, you'll be using it soon. And then routing protocols to route within a LAN. Your network access layer includes ARP, which we'll learn a little bit more about, your Ethernet, this is where your NICs are. So this is all part of the TCP/IP protocol suite. Okay, and this is explaining the process. So you see here, you click this diagram, as I talked to you earlier, so they've typed in the HTTP, okay, so that's the actual data itself. It's adding a header of TCP, okay, which is the port number. We have the port number for the web traffic, the IP address that's used, the MAC address, it goes out the NIC, it goes on the cable here, travels in ones and zeros and gets to the client. Then when it gets to the client, okay, it'll go in the opposite direction. So the client has received it. So they look at that MAC address, strip that off. You saw they just looked at the IP address. They sort out according to the port numbers or the protocols. and then the client can actually read the data itself. So there's the web page that pops up. I would encourage you to match these up. Okay, that'll help you in studying. Now, there's lots of different protocols out there. We have lots of different standards organizations, so I would encourage you to read each of these. You can click the little plus signs here to read on each of these. But all of these organizations played a role in determining the different protocols we have. For example, the type of cabling we use, we say it needs to be a certain number of feet. Well, who determines that? How do we know that? These standards organizations helped us with that. How about when you go buy a wireless router? You know, if you buy an 802.11 AC or another version, that it's going to operate a certain way because it's been standardized. That's why these standards organizations are so important. Here's another diagram of those, so please just kind of read through those. They'll explain a little bit more. I don't want to bore you by just reading each of the slides, but this is another common example here. So you see like the 802.11 group is the wireless group. Ethernet is 802.3, and there's various others here. Also, see, this is the cabling I was referring to, so that EIA, TIA, or TIA, EIA standard 568B says that the cables are going to be a certain order with the wire pairs, and they're going to work a certain way. So again, it just keeps the standardization among all the different vendors consistent. So that's why they're very important. And I have you doing the researching networking standards to kind of understand a little bit about the standards organizations and the importance involved in that. So that's where I'm going to end this one. And excuse me, and in the next video, I'll talk about your OSI and your TCP/IP models. Hope you found this helpful.